Okay, so we're going to do today the third and final diffusion lecture, part 3. Okay, so just to review, in our first lecture, the main equation looks something like this. The flux, so the amount of heat moving from one place to another in the x direction, is equal to a constant conductivity times the gradient in temperature. So the closer together the temperature contours are, the more heat's going to come through. And then in the most recent lecture, we looked at this equation relating to how the temperature is going to change with time at any particular place. And we use a different constant, diffusivity, and this also involved the temperature gradient, but the derivative of that. So basically the curvature, this is basically saying that if this is x and this is t, that the temperature at any given point is going to change more where there's a lot of curvature. So if you can imagine two cases. Let's so over here, let's say the temperature is like varying tremendously, right? So there's going to be a lot of change in temperature over here, not as much in this area, and hardly any, let's say, in a place where either it's there's no change in temperature, or if the temperature change is gradual. Like, not much is going to happen here in terms of you're going to have heat flux, certainly, but the temperature change in this area isn't gonna not much temperature is going to change there. So there's solutions to this equation, transient heat flux equation, and we worked with one of them. And I'm going to give you another example of a solution. So there's so this is another analytic solution. So this is one where there's like a exact algebraic equation to find the temperature at any given time and any given place. So it's an analytic solution for cooling of two adjacent infinite planes. And this is what it looks like. T, temperature over T naught, and we'll define that in a second, is 1/2 minus 1/2. And then we see this exact same, pretty much any diffusion equation is going to have this term in it. Any solution to this transient heat flow equation is going to have this air function of x over 2 square root of diffusivity times time. So here we have, let's define T naught. So where T naught is the difference in temperature, in initial temperature. So we're putting these two bodies together. Let's say we've got body A, body B. This is temperature, this is distance. Okay, so they're just like before. They're put next to each other, and then we're going to see the temperature evolve over time. But in this case, neither one is an infinite heat sink. Okay, so they're both gonna change. So we're gonna see something like, it's gonna look like that after a while. Okay, so T naught is the difference in initial temperature between the two bodies A and B where body B is initial temperature equal to 0. Okay, so we're just gonna, this equation works out easier if we just call this 0. T naught is going to be this difference in temperature here. And it's, if it doesn't have to be, you can solve this and then scale it. So you can, this applies to cases where body B isn't at 0, but this equation it's just simpler to just think about it when temperature of body B is 0. Okay, so a couple things. Let's just kind of look at this equation for a second. A couple notes. Note. The contact, so at x equals 0, so put a 0 in here, so that's going to be right here, so we're going to have x is 0, and then let's say this is x is 10, this is minus 10, okay? So at 0, right, the contact, you can put a 0, you can see this in Excel, put a 0 in for the air function of 0 is 0. You have the temperature is going to be 1/2 of T naught. Okay, so it's going to be right there, right in the middle. And it's not, this isn't temperature, this isn't time dependent. So it's going to sit there the whole time. Eventually, after a long time, all the temperature around here is going to be at 1/2 T naught. So that's another way to look at this, right? If we just put a huge number in here for time, that'll bring this term to 0. You'll get the same result. Let's say that at x equals n, or t is infinite, you get the same thing, okay? And let's try this at x. So let's say at x is infinity now. So x goes, we're really far away from this boundary. Air function of a really large number is 1. So we have 1/2 minus 1/2. We have 0 over here. So t will be 0. Okay, so in other words, t will be the initial temperature of body B. And just to get a sense a little less theoretical of what we're talking about, or sort of one example this could be where this would be relevant would be, let's write it here. Example, a large magma at temperature, intrudes a country rock. Okay, so at t equals 0. Okay, so like imagine this is like a granite that intrudes, and it goes into some rock that was colder. So the granite's going to cool down. The rock it went into is going to heat up. And there's many, this is just one example. There's many examples to this transient heat equation. So these have both been basically like one-dimensional examples, but there are also analytical solutions to three-dimensional problems. So, for example, like the cooling of a sphere. And I want to just make a couple notes on before we move along on the air function. So the air function of a negative number is equal to is minus the air function of that number itself. So if some versions of Excel, some older versions can't do this air function of a negative number, but you can just do it the normal way and then just make it negative. I think most of the time this isn't going to be an issue. And sometimes in these equations, you're going to want to solve for time or x, okay? So you're going to need to know, you're going to want to do the inverse of the air function. And this is not in Excel. But it can be calculated. And so it's equal to the square root. So if you type square root of gamma inverse, this is of x 0.51, and I'll show you in Excel. This returns the inverse air function. So let's shoot over to Excel and I'll demonstrate this. So let's say that we have a number 0.345. Okay, so it's easy to say, okay, what's the air function of that? Okay, it's 0.374. All right, but let's say we're in a situation where like we want to know what we have this value 0.374. We want to know, well, what could we have taken the air function of to get this? Okay, so that's when we type in equals the square root gamma inverse of this number 0.51, and I'm going to remove this extra e I added. Okay, and then we're back to the number that we started out with. Okay. So we're next going to talk about kind of cool aspect of diffusion called the characteristic length or the characteristic time. So this is when we want to just kind of get a rough estimate of how long or it's going to take for diffusion to happen, or what length scale we can expect to see the effects of diffusion. And we'll be talking in a minute also about not just thermal diffusion, but there's other sorts of diffusion as well. And this concept, characteristic length or time, applies there as well. So the basic idea is that order of magnitude characteristic times length can be calculated using the expression x squared, so distance squared equals 4 times diffusivity times time. Okay, and you might recall, so basically this is the term more or less that appears in these solutions, right, up here. So I've typically in-person classes did a demonstration, which wouldn't really be effective, as you'll see in a second. But I'm gonna just explain what happened. So how we could use this. So the diffusivity of copper, you can Google this. It's quite a bit larger than for rocks. It's around 10 to the minus 4 meters squared per second. So I had a little copper wire, and I had a student hold one end. So if you held the end of and I measured it, it was 0.07 meters long. And I had a student hold that end, and I lit a lighter on the other end. Okay, so the question was, how long is it going to take before it gets so hot that he's got to drop it? So how long would it be until it was too hot to hold? Okay. So this, of course, different people are going to, the question is, okay, well, what's too hot to hold? And different students are going to have different sensitivities to heat. And so this is we're talking an order of magnitude, okay? So the question is, like, is it going to be 10 seconds or 100 seconds or 1,000 seconds? Like, what, roughly, very roughly. That's the sort of situation where this sort of characteristic time and length. You want to just get a rough idea. And so to do that, let's just calculate it. You're solving for time. So time, in this case, x squared over 4 times the diffusivity. So this would be, we had 0.07 meters. I'm going to square this, divided by 4 times 10 to the minus 4 meters squared per second. Okay, so you can see that the meters squared are going to cancel. We're going to have seconds. And if we put that in the calculator, you get about 12.3 seconds. And it turned out to be remarkably close when we did this demonstration in class. So in any, we didn't need to do any differential equation or anything like that. Like this can come in really handy just to get a quick sense of how a diffusion equation, or diffusion problem. So we'll have you do a question, do one of these. Okay, how long would it take to heat the end of a rock with the same dimensions? So imagine I had a so point just 0.7, about 7 centimeters long, right? So 7 centimeter long rock. So take a moment, pause the video, and see what number you calculate. Okay, so it's the same equation as before, x squared over 4k. And in this case, the only thing different here is you went back, look in your notes, you remember that all rocks in magma have roughly a diffusivity of 10 to the minus 6. So about 1/100th of copper, and you get around a little over 1,000 seconds. So it's about 20 minutes, okay? And most of this difference so you might recall that the diffusivity has in it both the heat capacity and the conductivity. Most of this difference is coming from the conductivity. Copper is far more conductive of heat, about over 300 times, I think, compared to rock. I'm sorry, about 130 times larger for copper. So this is something that we can sort of confirm in natural situations. So so these often follow a square root relationship. So I'm just going to give an example of from the 60s. There's a lava lake in Hawaii, and so this would be depth. And this would be the square root of time. And what they did is they went out in this lava lake as it was cooling, and they measured the thickness is the thickness of the crust. So this is you can look at this is figure, actually it's figure 2.1 from Phil Potts' book, but you don't actually have that chapter. But in any case, the data that follow this square root relationship, very like a nice linear line going through. So in that's basically to first order, it's the characteristic equation. So the depth, the thickness x being proportional to the square root of time. And the same thing occurs for the depth of the ocean floor. Right. So when we draw those diagrams, so that we have like, okay, the ocean ridge. So we have spreading. I happen to have a nice blue color, so I might as well make the ocean surface be blue. At the ridge, where the rocks are hotter and less dense, the depth of the seafloor is shallower than it is further away, right? Because due to the cooling. And that relationship of ocean depth follows a very similar relationship with the square root of the age, in this case, how old the ocean crust is. So this would be like, 100 kilometers or something like that. Okay. So let's just look at this lava lake example just a bit more. So for example, we could ask, well, how long would it take to reach 7-meter thickness? Oops. Of crust. So again, it starts out as pure lava, but then it, due to the air, which is much colder, it solidifies, and it over time it gets thicker and thicker until there's no more lava left, right? So we would take that same equation, in this case, solving for time, x squared over 4k. Put in 7 meters squared and I'll just type this up. Get about a very big number. 1225 seconds. So we can just let's just go over to Excel real quick to see what that looks like in terms of months. 1225,0,0,0,0. Okay, so that's in seconds. So if we want to turn this into months, we'll start with seconds. There's 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, about 30 days in a month. Oops, I think I was supposed to divide by all this. That makes more sense. About 4 or 5 months. So the last topic we're going to cover briefly is chemical diffusion. So it's very analogous to heat diffusion. But in this case, involves a temperature-dependent diffusivity. Capital D. So the characteristic length and time equation is distance squared goes for, in this case, dt. So this makes sense. So it's basically like with heat diffusion, we had a diffusivity small k that was related to what the material was. So copper was much more diffusive than rock. But you can imagine that if you're talking about a situation where, let's say, like, I heard about a sculpture once where they had a layer of, I forget what the two metals were, but maybe you have a layer of like copper and iron or something like that. Okay, so over time, a little bit of copper is gonna enter into the iron, and a little bit of iron is gonna enter the copper, right? That's gonna be, the way that happens is the molecules bouncing back and forth, kind of like when we talked about diffusion creep. They mix, and that's going to be highly dependent on temperature. So that's why it's going to be dependent on the material, what if it's copper or stone or whatever, but also on the temperature. So let's look at an example calculation. The balance, it's just a geologic example, but as I said earlier, this diffusion theories applies like in many different sciences. So the balance of iron and magnesium between these two minerals, garnet and biotite, is strongly temperature dependent. These diffuse quickly in biotite, which we're just going to abbreviate BT, but slowly in garnet. So what we're saying here, basically, depending on the temperature, iron and magnesium are going to like to be at different concentrations when these minerals are next to each other. So you're going to want, if you turn up the temperature, for example, maybe garnet's going to enjoy having, it's going to want to have more iron than if the temperature was lower. And so the magnesium and the iron move back and forth depending on the temperature. And they're going to do that by diffusion. They're going to follow the sort of diffusion relationships that we've been talking about. Diffusion profiles in garnet, constrain temperature histories of rocks. So let's say we have a garnet. This would be garnet, and we have some biotite mineral near it. What will happen is we can analyze, and we'll see like, oh, there'll be like contours of iron magnesium ratios in the garnet, and so we can make a profile. Let's do another one here. Okay, so distance x, and we'll see, let's say we do a profile of iron, we might see that it does something like that. Okay, so we can look at this time scale, or sorry, this distance, and we could use like the characteristic equation here and figure out, okay, if we, how long were these things next to each other at a certain temperature. So let's do an example calculation, which is the titanium in quartz. Okay, so the diffusion so quartz is 99% silica and oxygen, but it does contain little bits of other things like titanium. So in the titanium will diffuse in the quartz. So that relationship is given by sort of we have to calculate. I said earlier that this diffusivity is a function of temperature. So for quartz, it works out to be 7 times 10 to the minus 8 exponent of minus 273 kilojoules per mole over R times the temperature. And the units, again, are meters squared per second, just like in heat diffusion. And R, is 8.314 joules per Kelvin per mole. So this equation tells us how diffusive, how easily titanium moves around in quartz based as a function of temperature. So the question, it's the sample question. So would you expect titanium in quartz to reset, like to change its composition, to adjust or diffuse in a 1 millimeter quartz grain at a temperature of 573 degrees Kelvin. So that's, in other words, 300 C. Okay, so this is actually from some work that I did, titanium and quartz. It was in Taiwan. So so basically, like there's a sedimentary environment. Okay, so some quartz grains, there was some granites that had been exposed, and quartz from that had been deposited in a basin. It's like some sand was deposited in a basin, and later this basin was buried underground, and it was heated up to a temperature of about 300 degrees. It was, the time period here was something like around 10 million years. And so the question was, like, if you have a quartz grain, so this is our sort of 1 millimeter grain. It's got this we'll make titanium a little blue, because it's got a certain concentration of titanium. When it's heated up, that titanium actually is going to be unstable. It's going to want to leave, or it's going to want to readjust, but it's going to only be able to do that if diffusion is possible. So to try to answer this question, we'll use that characteristic equation, right? So we could ask, okay, well, if a grain is this size, well, how much time would it take for it for that diffusion to occur? Okay, so the equation we'll just write it like this: how much time, and we'll start up here so we have room. X, so the distance is 1 millimeter, and it's, you could say, well, maybe we should use the radius. It's a spherical problem, but this is order of magnitude kind of calculation. So let's just use 1 millimeter, which is 0.001 meters. Gonna want to be in meters. It's going to be in the numerator. And then the denominator is going to be 4 times this thing, okay? 4 times 7 times 10 to the minus 8. It's 273 kilojoules per mole. Put in 8.314 joules per Kelvin per mole. (573 Kelvin). And let's check the units here. So we have kilojoules and joules. Kelvins are going to cancel. So we're going to say, so there's 1,000 joules is 1 kilojoule, right? So let's put 1,000 joules per kilojoule here, and then we can cancel all those units. This is not meters. This is moles. So the moles cancel, right? Moles. Okay, so that's all those units are going to cancel out. And I'm just going to type this in. Okay, 0.001. And try this yourself at home. See if we get the same number. I get about 2.8 times 10 to the 25 seconds, which is about 8.8 roughly times 10 to the 11 million years. Okay, so a huge number, huge time, older than the Earth. So the answer here would be no. We would not expect the titanium and the quartz to reset.